So good afternoon everyone. So we have seen like how we can able to calculate the dynamic stiffness matrix or spectral element matrix for a beam element using Euler-Bernoulli theory. So we saw that we write the equation of motion, just like if we quickly review that full thing. So we have written the equation of motion, then we have written the rotation, moment and shear force. We have defined the sign conventions. Then we started solving it using the principle of variable separation. Now once we do that, we get the equation in terms of W. We resolve that full thing in terms of W. We have seen either we can write it in terms of the e to the power series of the e to the power, like C1 e to the power of lambda x plus C2 e to the power minus lambda x plus C3 e to the power of I lambda x plus C4 e to the power of minus I lambda x. So that way we can write it, or else we can convert it into the sine, cosine, sine hyperbolic and cosine hyperbolic functions, and we can rewrite the full thing. Fine. So from there we have seen we can write that expression of the displacement field as like nx into c. You can think it very close like the shape function, but there is a small difference with the shape function versus this nx here. Shape function is usually written like ux once it is writing in form of the degree of freedom, means instead of c that unknown, if you are placing here u1 theta 1 u2 theta 2, then this one will be your shape function. Okay, but once it is c, then it is not exactly the shape function. Agreed? Got that point? But that can also be written like from here also, like this form we can also write that form. And there is another difference here, that is this e to the power of lambda x function, if you see, they are exact function. Normal cases in the finite element, once we are actually writing it in terms of the degree of freedom. So we are writing and we try to express and we try to assume some displacement profiles, and accordingly we are writing the shape functions and we solve it. But here the shape functions are first of all frequency dependent, and they are the exact solution of the governing differential equation. That is the important point. Okay, perfect. Any doubt? Good. So we can write like W, theta, M, V, all the things we can able to express in terms of C, and once that thing is completed, then we can express like all the force terms in the both of the side of the beam element, and all the displacement terms in the both side of the beam element and in terms of C, and then we eliminate the C finally and we rewrite the full thing. Okay, now if you want to see that what will be, so we have seen that our Wx is basically nx times C. Okay, and we know what is C. C equal to nothing but d inverse times d. And what is my d? D is my nodes or the degree of freedom, because d is nothing but your w1 theta 1, w2 theta 2. Okay, so if we do nx whatever we have written, multiply with the d inverse, then it can be converted. So this will be your shape function. Got that? Agreed? We can recalculate the function like this way. So this way we can get that function, all those things we can get it. I can write it w theta, this all those things you can get. Now once we got the function, means once we got the our stiffness matrix also, like our v1 m1 v2 m2 equal to w1 theta 1 w2 theta 2. So we can able to calculate the natural frequency of it. How? So we can do the two things. One is like we can able to find out the response, and second thing we can find the natural frequency. If you see, two are the two different types of problem. Why? Because in case of natural frequency, once we are trying to calculating, what we know. In case of natural frequency, it is basically a free vibration problem. So if we recall, our lambda, which is basically nothing but rho e omega squared divided by ei fourth root, that omega is what? In that, because all other terms, they are basically my property of the beam, but that omega is not the property of the beam. Omega is what? Excitation frequency. Now the question comes, in case of free vibration, where is your excitation frequency? And what are we calculating in case of the free vibration? Anybody try to recall? If you have a single negative freedom system, stiffness K, mass M, free vibration, what we try to calculate? Natural frequency, exactly. So here our target is to calculate that omega. So we don't need the omega, we will try to calculate the omega. Okay, agreed? So now think that full matrix, whatever we are getting, that matrix is nothing but the function of omega. It is nothing but the function of omega, because that is all the terms are related to lambda. If you see, full thing is related to lambda, and lambda contains omega. Agreed? So it is a function of omega. And what we have to do, what is another thing is important in case of the finding the natural frequency, that is what are the boundary conditions. Because if you think we have a beam, if we are holding it one side like a clamp, it will give the defined natural frequency. If we put it as a simply supported beam, it will give the defined natural frequency. If we make like one side pin, another side if we just make like a propped type of thing, it will give different type of frequency. So these frequencies are dependent on boundary conditions. So we need to implement the boundary conditions here. How can we do that? So let's say we are doing a cantilever beam. So like one side is fixed. So one side fixed means my W10, theta 10, let's say fixed, it cannot move. So these two terms becoming 0, and it's a free vibration, so I am not assuming there is any force. So what will happen? These two sides, the forces will be 0, F2 0 and M2 0. There can be force, because whenever you are having your degree of freedom restricted, there you will have a reaction. Suppose you want to do something and you are restricted to do that, what will you do? You will give the reaction force. Very simple. You can think it from your real life. You want to do something, your parents do not allow you to do that. You will show your reaction. Simple. That same thing happens for structures as well. Why not? So that way you can see that these two will also become 0. So there is 0, there is 0. Make sense? And once we have a matrix, we can also subdivide it. So if I think this is my S11, S12, S21, S22, and this is my F matrix, this is F1, F2, this is D1, D2, or means like this way. So can I write F2, which is basically 0, is equal to S21 into 0, or maybe S21 into D1 plus S22 into D2. Now think D1 is 0 and F2 is 0. So can I write it S22 into D2? 0 equal to S22 into D2. Now we know that D2 is not 0 because D2 is this side. This has a displacement, this has a rotation, so that is not 0. That means that end can move. So what should be 0? That is not 0. So my S22 should be equal to 0. And S22 contains what? That is containing the omega. So this is a function of omega. So now if we can able to solve the transient equation comes out of the determinant of S22 equal to 0, that transient equation if we can solve, we can able to solve what are the values of omega for which we are getting the S22 equal to 0. And these omegas are the natural frequency of that structure for this boundary condition. Can I say so? Yes, we can say that. Yes, here the prime challenge is where solving that equation, because these equations are often quite complicated because they are transient equations. Like you can see already, if you see, this is not that simple looking matrix having all lambda everywhere. If we take the inverse of it and we have to multiply with the F matrix. F matrix is also not that nice looking matrix. So that inverse multiplying with the F, you can think that they are with the expressions of like exponential type expressions. So solving them is sometimes challenging. So that is one of the issue happens here. So they are sometimes like you have to use some sort of nonlinear eigenvalue solution, Newton-Raphson type technique, or bisections, this type of technique you can follow. But still, once you are solving for omega, and if the omega value is real, that means there is no damping. If you are solving that way, then what happens? You can also able to just plot. What is the very simplest way to do that? If you do not want to go into any difficult methods, what you can do? You have that full expression, whatever the expression it is. So I generally do this way. Like whatever the expression of S22 omega comes, here is only one variable, that is omega. Nothing is variable. So I just plot that term. Here I take a logarithm. Then you can see that the graph will go like this. So wherever you will get a drop, that drop actually shows there the solution is going close to 0. And if we can identify those drops point, you can get what are the omegas. That's a quite easy way to do it. But that works when omega is real. Can omega be complex? Then why I say that omega is real? Think, what is omega here? Here omega is the natural frequency. Now think, can natural frequency be complex? It can be complex. But where? If you have damping. If you have damping, it becomes complex. Naturally it becomes complex. It is, we wrote it real. If you recall, suppose we are solving this system. We don't have to take anything very difficult system. Just take it like this. Equation of motion 0. Just 0 because we are solving for the natural frequency. What is x? Lambda t. So C 0. Lambda should be the root. Minus b. What is lambda? Now generally what we see, just like if I just divide it with the m, or maybe just so C equal to 2 xi omega m, if I'm just substituting, and k equal to omega square m. Then what can I write? Ah, 2, 4 will be cancelled out also. This will be the case. And now if you think xi is generally less than 1, there is a normal cases like for the undamped system, underdamped system. So you can see and if you think what is the natural frequency? Natural frequency is this one. That is the underdamped natural frequency. So omega d equal to what we say? Can you recall? Damped natural frequency. And what is this? This is the decay term. E to the power of minus xi omega t. The response get decayed with this term. Makes sense? So if you see here, your omega means here we assume that solution as like e to the power lambda t. So that's your omega. That omega becomes complex. So if there is a damping present in the medium can and if we try to calculate the exact natural frequency, we will get it complex. what do we do generally? We generally do not go in this way. We generally say, forget the damping, solve the mass and stiffness, get omega, and multiply with root over of 1 minus xi square. But come on, where the root over of 1 minus xi square came? Why are you multiplying it? And that is the exact logic, that root over of 1 minus xi square does not just came from nowhere. This actually came like that way. And it is the correct explanation of this, that how these things actually need to be solved. Got that point? So once we are introducing the damping, our natural frequencies will no longer remain real, they become complex. So therefore, if you think you are solving a damped system or damped system with for this type of solution, this method will not work. How will you do that? Then you have a real x, real omega, imaginary omega. It will become like a, means instead of having like a curve, it will become a surface. It's extremely complicated to solve it. There are actually some nonlinear eigenvalue solvers are there. They actually do this type of thing. They are like a specialized solver for doing that. And you can very nicely see that. Why not? Just have a look how it look like. So minus xi omega t into e to the power of I omega this. Came like that. Now you see this term do what? Decay. And this term is nothing but and this thing is omega t. So see, that act like a natural frequency. And previous term is actually decaying the full solution. So if you are actually allowing the roots to be complex, it can gives you the complete solution. But we generally do not allow it. We just do what? We say that, okay, forget the C. We just solve it like mx double dot plus kx. So from there, we came up with omega, and then just forcefully multiply with 1 minus xi square, root over 1 minus xi square. That gives my omega t. And we say, okay, xi e to the power of xi minus e to the power of minus xi omega t is the decay. So this thing actually hinders our like source of means that's the correct knowledge is actually get hindered due to that way. But if you just solve it in the correct manner, you can see that this thing comes automatically. Okay, makes sense. Good. So yeah, so I hope we got that idea that how we can able to implement this type of stiffness matrix method and how we can able to solve it. Good. Now here also, like what we have derived, you see, in this equation, first of all, can you tell me that whether this is damped or undamped? Undamped. Yes, this is undamped equation. There is also damped equation of Euler-Bernoulli mean. So if you take that damped equation, then you will see your omega will become complex. That's something very nice actually to do it with the damped Euler-Bernoulli. Now maybe you are thinking that okay, we have done this very good, but where is the wave? We have just little bit come out from the wave maybe. There is no periodicity, no wave, but it's a class of the wave. So what's happening? Actually, we just make the pitch to put the wave into it. So now let's see that suppose if there is a periodicity into it, then how we can able to redo the full thing. Okay, so So now let's think that you have a beam, let's say like this, and another small beam, again another large beam, another small beam. Like this way, the things is going like a periodic structure. Okay, how will we solve? So first we make the stiffness matrix. We try to understand how to formulate the stiffness matrix. All those things are done. Now let's think, if they are arranged in a periodic manner, how we can incorporate the Bloch theorem and try to solve it. So now if we think that we are now, what we did, we have seen that like if we have a beam, these are the degree of freedom, how we can able to write the stiffness matrix for that in the dynamic domain. So where the frequencies are also inside it. Okay. Now if we think that, so that we have able to see that. So now just let me draw the degree of freedom. So so this is the node 1, node 2, node 3. So that is my unit cell. This is my unit cell. Agreed? So what should I have? This one is like going up. So my bending moments are like this one. So you can think that these two and these two are basically periodic. If you recall, we have a periodic cell, so left side and right side, or not left and right, left to the next unit's left should be periodic, right to the next unit right should be periodic. There we can implement the Bloch theorem. So whatever is my state vector x for n, there that Bloch theorem exists. It is the power of I mu. That thing exists. I just write the state vector. So phi, now what you, that phi x that contains wx, theta x, mx, vx. That is the state. State means what are the vectors associated with that. So that has degree of freedom and its force derivatives, or its force, not derivative, its forces and displacements. So displacements are transverse displacement and rotation, and in the force shear and bending. Okay, fine. So we got that. Now you think this thing will be equal to this. Now if we recall, in the last case we have written that wx as like nx into cx, I see theta x is also n dash x into c, mx equal to ei into n double dash x into c, and vx equal to ei into n triple dash x into c. Agreed? Agreed? So can I write then See, nx is like a 1 cross 4. So this is 1 cross 4. So once I am making it, this will become 4 cross 4. And my C is 4 cross 1. So finally I getting it 4 cross 1 vector. Agreed? Agreed? And here you can see that I do not need to change the rotation like what we did here previously. If we recall that we have added that minus, these two minus we have added because left up, right down and sagging. But here we don't need to do it because whatever it is, we are just taking it. We are not try to find out the stiffness matrix. We just try to find out what are the state vectors and how they are correlated with the unknown vector. Agreed? So we are not changing anything. We are not trying to finding out what is the at the edge. I am just trying to understanding. I'm just trying to understanding what is there at any point, how we can able to write it. Agreed? No problem. Now, good point is where, suppose if I put phi n 0, then what will be the direction of all those things? So my displacement will be upward. If I think the phi n 0 left side, so what will be that? Displacement upward, rotation anticlockwise, shear force upward, bending moment clockwise. That will be the naturally this thing will come. Or maybe I'll just do one thing. I just draw the forces with the red. Okay. And displacements are with the black. Okay. So this is my V. This is my M. This is my W. This is my theta. So that thing is happening there. Okay. Now think what is happening so that I can get it from here. Just if I substitute that and I can get it. No issue. Now if I try to calculate phi n L, what it will be? Just think like we are calculating it here. How much it will be? So that also you can just place L here. Instead of X I can place L. I will get it. But what will be the directions? If we are taking it in the right, then the direction will be, this will be same, and these two will be opposite. Okay, this will be coming in the right side. So right side, if I just put it R, and if I just put it left side as L. Okay, fine. Agreed? Now think what is happening at n plus 1, 0, left side. Now think very carefully. When your right side is finishing and your left side is starting. Okay, so that this element is finishing here and these elements left is starting. So here how your shear force is acting? Downward, and bending moment is going like this. So that is the positive one. What you are getting from here? This thing is telling nothing but this. And what is the left one? And think at that junction your bending moment and shear force should be matched, isn't it? So they should be matched. So what will happen? these two will be equal and these two will be equal. Means your shear force will be equal, bending moment will be equal, and shear force will also be equal. Okay. And what happened with the displacements? Displacements was like this. Displacement should be equal. Displacement should not be balanced. Displacement should be equal and forces should be balanced. So for having the forces to be balanced, you see already your assumption is allowing that thing that forces are automatically taken in the opposite direction. So they get balanced automatically, and displacements all are in the same direction. So they are automatically becoming equal at that junction. So you don't need to be worried that much. So you can write what? Phi n plus 1, 0, left side is equal to phi n L right side. Can I write that? Please pay attention and think it. Because shear force and bending moment we can only see once we make a cut. If we do not cut, we cannot see shear force bending moment. Sure short. So once we cut it, then it has a left side, right side. Okay. Now left side, what happening? Shear force is going up, left up is positive, and bending moment is clockwise. In the right side, what happened? Cutting, shear force is going downward, and bending moment is anti-clockwise. Now at that junction, what happened? Left side, bending moment is clockwise, and right side bending moment is anti-clockwise. So that clockwise bending moment and anti-clockwise bending moment at that same location is balancing each other. And shear force is also doing the same thing, upward and downward. So at that junction, they are equal and they are balancing each other. Sorry? Yes, and that's the beauty actually. Like if you are assuming it in this way, you will end up with that, and that will cater that full thing. So that's why what I told at the very beginning, that it is better to follow that sign convention. If you change the sign convention, your equation of motion and all those things get changed. But you have to again see that whether this thing is happening or not. Okay, but with this sign convention, this thing will automatically happen. Okay. But whatever the sign convention you follow, once you are cutting, they make it like that way, that once you are cutting it, it will automatically come. Until unless you came up with something very crazy sign convention, which I think quite difficult to get. Okay. So this thing we can assure that these two will become equal. Okay. Okay. And additionally, another important thing, we have that beam, second beam. So node 1, 2, 1, 2, but L, R, nth element, n plus 1th element. So what we can see, phi n L, yeah, okay. This is 0, L, 0, L distance mein. So that is the left side, right side, left side, right side, left side, right side. So phi n 0 left side, phi n plus 1 0 left side equal to phi n to the power of I because of Bloch theorem. So whatever is the displacement here and whatever the displacement here, if we remember that Bloch type thing, we are assuming that a single wave is going in that space, so they are correlated. Displacement, bending moment, shear force, all are actually vectors. So these all vectors can follow that Bloch theorem. So they are getting correlated. Next thing what? So next thing is that we have also seen phi n r. The transfer matrix. How the transfer matrix comes into picture? Transfer matrix, we can think that phi n, phi nl, we can calculate the phi nl because we have nx, n dash x, n double dash x, n triple dash x. We see. Okay. So if I put x equal to L here, I can get, so I can call it as like NL matrix. Okay. And if I do in zero matrix or maybe in L matrix, what means in bar. So in bar, zero matrix, we see. So what will happen? Phi n L equal to NL into N0 inverse phi N0. So now if I just substituting there, and this thing is equal to phi n plus 1 0 left should be equal to that we have already shown. Why this thing is happening? Because that's the junction. This junction, this in these junctions, they are equal. So what can I get? So if I just substituting, so this is, I am calling it as a T matrix. Will be equal to the power of I mu times I. So these and these, they are equal. So NL into N inverse 0 should be minus e to the power I mu times I, that is equal to 0. And in that NL, there is your frequency. In that NL, what are there? Yeah, there is the omega term and there is a mu term. So here you can able to find out omega versus mu, and you can able to get the dispersion plot. I think I should stop here now. I think it is getting too much. I think we can stop here. In the next class, we can start from here. We will redo it, and from there we can proceed.